Okay, so this section is for 4.1, and we're going to be talking about maximum and minimum values. So what this definition essentially says is we have a function defined on some interval d, and the absolute maximum is the value that is the greatest, and the absolute minimum is the value that is the smallest. We call them an absolute extreme value when it's either an absolute max or an absolute min. Okay, so the takeaway from this definition is absolute max is going to be the highest. And then your absolute min is going to be the smallest. Okay, so it's going to matter how your graph is defined. So I'm going to show you a few pictures. So the existence and location of your absolute max and min is going to depend on the interval that you care about and the actual function itself. Okay, so if we look at this first graph here at A, your absolute min is going to be here at x equals 0 because that's the lowest point. And we're not going to actually have an absolute max because this is going to keep going forever and ever and ever. Okay, so but if we look here, this graph is defined only on the interval between 0 and 2. So since I only care about between 0 and 2, I still have my absolute min at x equals 0, but now I have an absolute max of 4 when x equals 2. So let's look at a few more things. Okay, so here, notice we don't have an absolute min, and we don't have an absolute min because there's a hole here. And our absolute max is still going to be 4. And then here, notice we don't have an absolute max or min because there is a hole at both x equals 0 and x equals 2. All right, the other thing that I want to draw your attention to is when we have discontinuity. So we've got an absolute min here at 0 and also at 1, but there's not going to be an absolute max because that is undefined. And then here we have an absolute min. This is our lowest possible point, but there is no absolute max because we've got a jump here. Okay, so we have to watch out for those as well. Okay. So we got another definition I want to talk about. Oops. So the extreme value theorem, I somehow managed to get on the eraser, is it states that a function that is continuous on a closed interval has to have an absolute max and an absolute min at some value on that interval. Okay, so what it's essentially saying is it's going to be continuous, which means there's no jumps and no holes. Okay, so even if I had something like, here, let's get this, and let me switch colors. Let's say I had something like, okay. So we only are looking at this interval here between, I don't know, negative something and positive something, right? It's telling me that because it's continuous and I have a closed interval, there has to be an absolute max and it has to be an absolute min, okay? So let's see that in action. All right, so for these two functions, what we're going to do is we're going to identify the absolute max and the absolute minimum value. And we're going to see if the functions meet the conditions of the extreme value theorem. So remember, it has to be continuous on a closed interval. Okay, so if I am looking at the first picture, is it continuous? And the answer is yes. Okay, so boop, 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 boop. Continuous. Is it a closed interval? Yep, because we're just talking about from A to B. All right, so then the question is, do we have an absolute max? And the answer is yes, our absolute max is right here. So if we were gonna write that as a point, since I don't actually have numbers, I have just A, we're gonna say A and the value of your function at A, since we don't know what it is, and that is our absolute max. And then our absolute min is here, this little divot, okay? So absolute min is the value of C and the function when you plug in C. All right, so notice because the first graph here was continuous and closed, we had both an absolute max and an absolute min. All right, now if we look at the second picture here, it's not closed because I've got holes here, and it's also not continuous because I have this jump here, okay? So this does not follow the mean value theorem, okay? Not closed, not continuous. Okay, so this means I could possibly not have an absolute max and not have an absolute min. And so I definitely don't have an absolute min because this is undefined, but I do have an absolute max here, okay? So my absolute max is gonna be C and the function value at C, okay? All right, so let's look at another picture. Loading, loading, loading. Okay, so we also have something called a local max and a local min. So when we say local, that means it is going to be like a hill or a valley that where your graph is going to change directions from, say, increasing to decreasing. So you'll notice by looking at this graph here, our absolute min is still going to be the absolute smallest value, but we also have a local maximum here, a local minimum here, because this is not as low as the point at A. So when we say local, it's going to be either a hill or a valley, but it's not going to be the absolute. Now, one thing that they will say is they will call your absolute minimum also a local minimum. So it will have two names, absolute minimum and local minimum. Okay, so let's get a formal definition. So our formal definition is a point that is smaller or larger, depending on if we're doing minimum or maximum, than the surrounding points. So how I like to remember this is when your graph changes from increasing to decreasing and vice versa. The other thing that you're going to hear this called is a relative max or relative min. Okay, so let's put this all together. All right, so we have a nice picture here defined along the interval A and B. And it wants us to identify any of the locations of maximum and minimum and use the terms absolute and local. Okay, so one other definition I want to give you before we do this problem is the word extrema. So what extrema means, it's the collective name for all of your maximum and minimum values. Okay. Okay, so let's look at this first. So I see an absolute min, the lowest possible point here at P. So what we're going to say is that there is an absolute min, but also a local min, because if it's absolute, it is also local at P. There is a local min at point R. Okay. All right, now let's deal with our max. So we don't have a single maximum here. We have an absolute max, which means we also have a local max. At both Q and S. And since my graph ends here at A and B, there is no max or min at B. So we say for points A and B, there is no extrema. And the reason why this is because if you look at your graph, it stops, okay? So it's not, it doesn't continue on. So we don't know, just based on looking at this, like if the graph continues down like this, or if it goes back up. Since we are only caring about this section, we can't say that there's a max or a min at point A and B. Okay. All right. So you're probably a little bit tired of your derivatives, but we still have them. So the local extreme value theorem, what this is going to say is your function is going to have a local max or a local min value at C. If the derivative of the function C exists, then the derivative of the function at point C is going to be 0. So remember, what we're looking at with this is, like, let's say we have something like this. The tangent line is going to be like that. And what's going to be the slope of that tangent line? It's going to be 0. Okay. So the slope of that tangent line is going to be 0, which means your derivative then can be equal to 0, so that we can solve this. Another definition that we're going to talk about is a critical point. So a critical point is an interior point in the domain of C. I'm sorry, an interior point C in the domain of your function f, which the derivative is going to equal 0 or the derivative is going to fail to exist. If it fails to exist, that is a critical point. And I'm going to show you what I mean with a real example in a second, but let's just take a look at some pictures. So, if we look at this first picture, we have a local minimum at C here, but the derivative of the function C is not going to exist because there's a hole. The other thing that we dislike is when we have these sharp corners. We're not allowed to have corners. So there is a local max, but the value of the function here does not exist. All right, so let's look at two more different kinds of pictures. So here, we're going to be talking about the converse of the local extreme point theorem, which is pretty much the extreme point theorem, but you're going to switch the order, okay? So this is not necessarily true because here, the slope of your tangent line is going to be 0, but there is no local max or min. And the same thing is happening here. There's not going to be a local max or min. Okay, so let's get into the good stuff. Okay, so for this problem, it wants us to find all of the critical points. So the first thing that you're going to do is you're going to find the derivative. Yay! Okay, so we have a quotient. So let's see. Low is going to be x squared plus 1. D low then would be 2x. Oops, 2x. Your high is going to be x. D high is 1. Okay, so remember we're going to do low D high minus high D low. Draw the line and square the low. Okay, so now that I have that, let's go ahead and plug all this in. I'm going to switch colors. All right, so low was x squared plus 1. D high was 1. High was x. And D low was 2x. All right, so then we're going to say x squared plus 1 squared. Okay, so let's simplify this a little bit. We're going to get x squared plus 1 minus 2x squared, all divided by x squared plus 1 squared. All right, so then we can simplify the top, and we're going to end up with 1 minus x squared, all divided by x squared plus 1 squared. Okay, so that was nothing new, right? So what we're going to do now is we are going to set this derivative equal to 0. Okay, so okay, so let me give myself a little bit more room. Oh, okay, so 1 minus x squared. Okay, so essentially what I'm going to do is I'm going to cross multiply, and this denominator is going to be multiplied by 0, so it's essentially just going to go away. So I'm going to get 1 minus x squared is equal to 0. I can then add x squared, and I'm going to get 1 equals x squared, and then I'm going to take the square root. And remember, when you take the square root, it's plus or minus 1. Okay, so now what I'm going to do is I am going to plug in positive 1 and then negative 1 to my original function. So plug in to original to get the y coordinate of the point. Okay, so when x equals 1, I'm getting 1 divided by 1 squared plus 1, which is 1/2. So I have 1 comma 1/2. And then I'm going to plug in negative 1. So negative 1 over negative 1 squared plus 1 is going to give me negative 1/2. So negative 1, negative 1/2. All right, and then if you plug in your original function into a graphing calculator or Desmos, you will see that the first point is a local and absolute max. And the second point here is a local and absolute min. Okay, so let's do a few more examples. Okay, so here is just a couple of steps to keep you organized. So first, you're going to find any of your critical points where your derivative is equal to 0 or it doesn't exist. And then you're going to evaluate the function at the critical points and at the endpoints. And then you're going to choose the smallest and largest values from that second step to be the absolute max and min. Okay, so let's see this in play. Okay, so step number 1, we're going to find the derivative. So that's going to be, 3, no, not 3, 4. Oh, what the heck did I just do? Oh, there we go. Okay. Here we go. And all right, so 4x to the third minus 6x squared. All right, fantastic. So we're going to set this equal to 0. So set equal 0. So that's going to be 4x to the third minus 6x squared equals 0. All right, so hopefully you see that we can factor this. So I can take out a 2 and an x squared. So I'm going to say 2x squared, which is going to leave me with 2x here and minus 3 from my 6x squared. And that still equals 0. So now I can set each of these equal to 0. So 2x squared equals 0, and 2x minus 3 equals 0. All right, so if I solve this first one, I'm going to end up with x equals 0. And if I solve this one, I'm going to add 3, and then I'm going to divide by 2. So x is going to be 3 over 2. So then what I'm going to do is I'm going to take these 2 points, and I'm also going to use these 2 points to evaluate my function to find the absolute max and min. Okay, so there are 4 total numbers that I have to deal with. x equals 0, x equals 3 over 2, x equals negative 2, and x equals 2. And I'm getting these last two from the interval, okay? So if I plug in 0 to my original function, 0 to the 4th power minus 2 times 0 to the 3rd power, I'm going to get 0. It's supposed to be an arrow. I don't know what's going on. That's a little bit better. Okay. If I plug in 3 over 2, so I'm just plugging this all into the calculator. I'm not going to write it all down because it's too much. I'm going to get negative 27 over 16. So essentially I'm doing 3 over 2 to the 4th power minus 2 times 3 over 2 to the 3rd power. All right, negative 2, I'm going to get 32. And when x is 2, I'm getting 0. Okay, so from here, what you're going to do is you're going to pick the biggest and the smallest, and that's going to be your absolute max and absolute min, respectively. Okay, so the smallest value is here. So, oh geez, I didn't mean to write on it. Take 2. Oop. Okay, there we go. All right, so absolute min is going to be 3 over 2, negative 27 over 16. And then the biggest value is 32. So that means our absolute max there you go. Okay, so let's do another one. Okay, find the absolute maximum. All right, so for this one, a little bit of a pain in the bazunga, we have the product rule. Yay. All right, so what I have to do is I'm taking the derivative of the x to the 2/3, so that's going to give me 2/3 x to the negative 1/3 multiplied by my original 2 minus x. And I'm going to add that with x to the 2/3 times the derivative of the 2 minus x portion, and that's just going to be negative 1. Okay, so let's simplify this a little bit. The negative 1/3 is going to drop down to the 3 with my denominator. So I'm going to get 2 times 2 minus x all over 3x to the 1/3 minus x to the 2/3. Okay, so this is a little bit yucky in the sense that I have a fraction here. So what I'm going to do is I'm going to multiply the right term by x to the 1/3 so that I can make the fractions have like denominators. All right, so what's going to happen here in this numerator, though, is 2/3 exponent plus 1/3 is going to be 3/3. So essentially that's going to be 1. So that's just going to be x. And, oh, you know what I forgot? I forgot the 3. So I'm not just multiplying it by x to the 1/3. I need to multiply it by 3x to the 1/3. So this numerator is going to simplify down to just give me 3x, and then I can write my denominator over 3x to the 1/3. Okay, so let's see. We've got, I'm going to distribute this. 2 times 2, which is 4, and 2 times negative x. So we're going to get 4 minus 2x minus 3x, all divided by 3x to the 1/3. So let's simplify this down. I have a negative 2x and a negative 3x, so I'm going to get 4 minus 5x, and that is all going to be divided by 3, and this is actually the cube root of x. Okay, so there's my derivative. It's a little messy there. Okay, so now that we have that, one thing that I want you to notice is since we have a fraction, we know that we cannot have 0 in our denominator, okay, because we are not allowed to divide by 0. So that means f prime of 0 is undefined, which means x equals 0 is a critical point. Okay. All right, so I can't really do anything else with the denominator, but what I'm going to do is I am going to set my numerator equal to 0. Okay, so then if I solve that, I'm going to get x is equal to 4/5. All right, so now I have all of my points. So we're going to evaluate the original function at x equals 0, because that's my critical point, x equals 4/5, because I just got that when I set my numerator equal to 0, x equals -1, because that was one of the starting points of my interval, and x equals 2. That was the other point of my interval. Okay, so when x equals 0, when I plug that into my original function, I'm going to get 0. When I plug in 4/5 to my original function, I'm going to get about 1.03. When I plug in -1, I'm going to get 3. And when I plug in 2, I'm going to get 0. Okay. So what this is telling us is we have an absolute max and 2 absolute mins. Okay. Ooh, I don't want to switch to that color. Okay, so my absolute max is here. Okay, sorry. Okay, there we go. Pen is not wanting to work anymore. All right, let me use the typing. Boop. Okay. -1, 3. Yeah, one more example. So I hope my pen will work for the last example. So we are launching a stone vertically upward from a bridge 80 feet off the ground, above the ground at a speed of 64 feet per second. If its height above the ground t seconds after the launch is given by the function f of t equals negative 16 t squared plus 64 t plus 80. For the interval 0 to 5, when does the stone reach the maximum height? Okay, so what this is telling us is we care about the absolute max since we're doing maximum height. Okay. All right, so the first thing that we're going to do is we're going to find the derivative of f. Oh, come on, pen. I just need you to work a little bit more. Okay, so we have negative 16t squared, which is going to give me negative 32t plus 64. Okay. So what we're going to do is we're going to set that equal to 0. So negative 32t plus 64 equals 0. So I'm going to subtract 64 to both sides. Oops. And so I'm going to get negative 32t equals negative 64. And then I'm going to divide by 32. Negative 32, which is going to give me t equals 2. Okay, so what I'm going to do now is I am going to plug in for t equals 2, t equals 0, and t equals 5. T equals 0, t equals 2, and t equals 5. Okay, so when I'm plugging in t equals 0, I'm getting 80 feet. When I have t equals 2, I'm getting 144 feet. So I'm plugging in 0 to my original equation, that's 80, plugging in 2, so negative 16 times 2 squared plus 64 times 2 plus 80. And then I'm plugging in 5, and I'm getting 0 feet. All right, so the maximum height occurs at t equals 2, so 2 seconds. The maximum of 144 feet and that's it. Done.